Hi guys, welcome to 6.3, the start of our last unit, which is called Advanced Topics. So this is our first section, and I apologize, this video I know will be lengthy. Many of you might have already seen a lot of this in your science class, but I have to go through it assuming that we've never seen it before. So if there are parts that you already know, well, that's great for you. All right, so again, I wrote out the notes and I'll take pictures of these and post them too. So some quantities have both magnitude and a direction and therefore cannot be represented by a single number. These quantities can be represented by a directed line segment. So again, when you have a quantity has magnitude and direction, that's a directed line segment. It has an initial point P and a terminal point Q. That's just the two letters we use to denote that. Its magnitude, denoted here with the double lines, and V, standing for that directed line segment, can be found using the distance formula. So if we ask for that distance, that magnitude, you're just using the distance formula. So here's a visual. This is your directed line segment from point P to Q. This is how I would denote the magnitude of PQ. Again, note that notation there and how it's drawn with the arrow, showing the direction that it's going in from P to Q. So here we go with vectors, the set of all directed line segments that are equivalent, meaning that they have the same magnitude and direction to a given line segment is called a vector V in the plane. Okay, so for these directed line segments to be equivalent, they have to have the same magnitude and direction, and we call these vectors. So let's jump into this. Here we go. I'm not doing very well with my camera work today. All right, so number one, let V be the vector from 0, 0 to 4, 5, and U be the vector from 2, 3 to 6, 8. Usually these are bolded in, and there's just so much to bold here. Anytime you see V and U and it's referred to as a vector, we usually bold that, just so you know. Okay, so we want to show that V is equal to U. So to be equal, up here we said they have to have the same magnitude and direction. So we mentioned above that magnitude would be, to find the magnitude, it's the distance formula. So distance formula is when you take the difference in the x's, you square it, and then you add the difference of the y's. So for V, just to really show you, you're doing 4 minus 0 squared plus, what's the other one here? 5 minus 0 squared. That's going to give you root 41. And that is the magnitude of vector V. Now we find the magnitude of vector U. So U is going from 2, 3 to 6, 8. So I just need to stay consistent. 6 minus 2 quantity squared plus 8 minus 3 quantity squared. And if you simplify that, great. Oh God, I meant to do it. I was in my mind, I'm like, oh, I'm going to do a check next, and didn't finish writing the one. Okay, so the magnitudes are the same. Now I need to show that the directions are the same. And when we're talking about directions, that's really talking about slope. So the slope between these 2 points, that would be 4 minus 0. Oops, nope, wrong one. Sorry, 5 minus 0 over 4 minus 0, so that would be 5/4. And then here I'd be doing 8 minus 3 is 5, 6 minus 2 is 4. So the directions are the same as well. So they are equal. There you go. All right. More notes / things for me to go through here, and terminology that we need to know. So a vector is in standard position. Think of how we talked about standard positions with angles, okay? If its initial point is at the origin. So that kind of makes sense. That's consistent with what we've said all along here through this course. All right, component form of V. So this is a specific problem when we'd be asking you for write the component form. You need to know what that means. So if V is in standard position, so meaning its initial point is at the origin, and its terminal point is at V sub 1 comma V sub 2, then V, that vector, can be uniquely represented as V equals, these are little arrows there, okay, not parentheses, V1 comma V sub 2. So that's if it's in standard position with its initial point at the origin. But in general, if v is any vector from some point x sub 1, y sub 1 to x sub 2, y sub 2, then its component form is you just subtract the x's, second x minus first x, comma, second y minus first y. Easy as that. There are some specific vectors that we need to talk about. The zero vector is when the initial and terminal points are at the origin. So again, this would be a bolded in 0, kind of hard to do here, but I guess not that hard. So 0 equals your component form 0, 0, and it has a magnitude of 0. Obviously, you could see that. Again, formally magnitude, what are you doing when it's in component form? You're just squaring your first plus the square of the second. And that's it for component form. A unit vector has a magnitude of 1, and we're going to get more into unit vectors here in a minute. Okay, example 2, applying what we just talked about. Find the component form and magnitude of the vector from the point 2, -4 to 5, 7. All right, so component form, I'm going to have v equals. So it just said to subtract, take the difference of the x's and take the difference of the y's. So I'm going to have 5 minus 2, comma, 7 minus a -4. Okay, so my component form is going to be 3, 11. Again, make sure you use those arrow notation there. Not really arrows, whatever you want to call it. So that's the component form. Now we want the magnitude. So make sure you use the proper notation there. So to find the magnitude in component form, you're just squaring v sub 1 and v sub 2. So you're just doing 3 squared plus 11 squared. So you're going to simplify that, root 130. And that's your answer for that piece. Okay, again, I told you this was going to be long. I'll try to stop doing side comments. All right, so vector operations. So if we let u be the vector u sub 1, u sub 2, and v be the vector v sub 1, v sub 2, and a real number k, which is your scalar, then if we are adding the two vectors together, it pretty much makes sense. You're going to add your first two positions in u and v, and then add the second position in u and v. If I have some scalar multiplied by the vector, you can keep that scalar outside, but you can also distribute that into u sub 1 and u sub 2. So that should pretty much make sense to you. Geometrically, what do these look like? So k sub u is a vector that is the absolute value of k times as long as u. It would be in the same direction if k is positive, k is greater than 0, and the opposite direction if k is negative or less than 0. So for an example, this is not drawn to scale, I just did a little sketch, but if this was your vector v, if your scalar was 1/2, so 1/2 v, it's just half of the distance of your original v, but in the same direction because k is positive. If you had a negative v, your k is -1, so it's the same length as v, but going in the opposite direction. Notice you need to put the arrows to show your direction. And then -1/2 v would be going, again, it's half of v, but in the opposite direction. Pretty much makes sense, I think. Okay, so geometrically, u plus v is the vector formed by the initial point of u and the terminal point of v, when the initial point of v is placed at the terminal point of u. So again, this is not drawn to scale, so bear with me. But if this was vector u and this was vector v, what is that saying? If you actually found geometrically u plus v, so it's saying you take the initial point of v and you place it on the terminal point of u. So here's u, here's the terminal point of u, and it said you have to place the initial point of v here. So we're kind of rotating v and putting it over here. This resulting vector, again, it says it's formed by the initial point of view, which is right here, and the terminal point of v. So that dotted line with the arrow here, that would be the vector u plus v. That's what that is saying above in words. Okay? I'm sorry for all the notation, but it is necessary here. So if vector v in component form is v sub 1 comma v sub 2, then just like we talked about before, negative v, you just distribute in that negative to each term there. So if you're doing u minus v, that's really just u plus a negative v, which you're just subtracting, again, the first terms and the second terms. This would be a vector from the terminal point of v to the terminal point of u. So this is a little bit of a different drawing here, but so if this was vector u and vector v, okay, the resultant vector of u minus v, it says it's a vector from the terminal point of v to the terminal point of u. So here we go. That's that visual. Again, u plus a negative v, just to show it u plus a negative v. Technically they're the same distance. This would be negative v because it's meant to be the same distance but going in the opposite direction. This would be u plus a negative v, just as a visual for you. All right, example 3, using these properties. So those are your two vectors, they're u and v. We want you to find 4 times u. So that's really just as easy as multiplying vector u, the two pieces, by 4. Good, so now we play the battery game. Okay, so you're going to get negative 20 and 8 because you're doing negative 5 times 4 and 2 times 4. And that's your answer. B, you are just going to add together the two pieces. So negative 5 plus 6, that's going to give you 1. 2 plus a negative 3 would be a negative 1. And then your last one, C, 2u minus v. So personally, I would just choose to do the 2u. Well, not personally, you actually should. So that's going to be negative 10, comma 4. Okay? And then you're subtracting 6 and a negative 3. So I'm going to get negative 10 minus 6. So that's going to be negative 16. And then 4 minus a negative 3, that's going to be 7. So there's your answer in component form. All right, so some properties of vectors. This is also found on page 451. Just really quick, your commutative property applies as well as the associative property. Please note that u, v, w here are all vectors. Over here, c and d are scalars. But if you add the 0 vector to u, or any vector, you get back that vector. Adding a vector to its opposite gives you the 0 vector, which makes sense. If you're multiplying some scalar times a vector, again, the commutative property, the associative property of a multiplication works. Hopefully you can hear this rendition of ABCs in the background. Laughing. Maybe you can't hear it. This is the distributive property. C and D are scalars. You can just distribute that into vector u. Same thing here. If you're adding two vectors together, you can just distribute in the scalar to both vectors. Obviously, if you have you have vector of 1 times u, that's just u. Same thing here. 0 times the vector u is just 0. And if you're taking the magnitude of some constant times vector v, you can just take the absolute value of c times that magnitude of vector v. Again, I don't need to bore you with those. At any rate, here we go. I can't keep a straight face through this with my kids singing in the background. All right, unit vectors. I said we were going to come to this, and here we are. So if v does not equal 0, again, v is a vector, then the unit vector in the direction of v, we denote as u, it's equal to vector v divided by the magnitude of v. Another way to write it, if you want, is vector v times 1 over the magnitude of that vector. So just some points here to keep in mind with unit vectors. The unit vector has the same direction as the given non-zero vector v. It has a magnitude of 1. I'll show you that in a second in an example here. It's usually used to specify directions, so there's no dimensions or units like other vectors. And it's the basis for expressing any vector having the same direction but an arbitrary length. All right, so here's an example applying that. So number 4, find the unit vector in the direction of 3, negative 4. All right, so to find the unit vector, we need to know, well, what is the magnitude of v? So let's do that first. So that's going to be the square root of 3 squared plus quantity negative 4 squared, which would be 25, so root 25. So the magnitude is 5. So to find u, my unit vector, I'm just doing 1/5 times the vector v, which is 3, -4. We do ask that you distribute it in and write it in component form, so it would be 3/5, comma, -4/5. That's your answer. Now, why does this, just as a side note, the magnitude of 1, right? Because if I actually found the magnitude of this vector, I would be doing 3/5 squared plus -4/5 squared. So that's going to be root 9 over 25 plus 16 over 25, which is root 25 over 25, which is just 1. So it does work. I know that wasn't a proof, that was just an example. All right, so but standard unit vectors, there are 2 of them, I, which is denoted as 1, 0 in component form, and j, which is 0, 1 in component form. This is what they look like. I, since it's 1, 0, that's over here. J looks like that. So sometimes you'll be asked to write your vector with standard unit vectors. So just, this is kind of a mini proof, not really, but so if this is your vector in component form, you can rewrite this as v sub 1 times 1, 0, because if I distributed that in, that would just be v sub 1 and then 0, plus v sub 2 times 0, 1, because that would be 0 v sub 2, and if you add those together, you'd backtrack. So by definition, 1, 0 in component form, that's just I, and 0, 1 by definition is j. So again, this is how you can write it using the standard unit vectors. Okay, just as a note, v sub 1 and v sub 2 are the horizontal and vertical components, okay, j and I, of v. And v sub 1i plus v sub 2j is a linear combination of the vectors of I and j. So another way that we could word it for you. So number 5, express your vector 3, -4 as a linear combination of the vectors I and j. So there's really not much work to show. You just need to realize that, oh, I have my first value here that I multiply by I. So I have a 3, so I'm going to write it as 3i, and then minus the 4j, and that's it. Really straightforward. All right, moving on to, I feel like sorry, I had this backwards. Okay, I apologize. Here we are. All right, so direction angles. So if u in the component form is xy, and that's a unit vector in standard position, and theta is the angle in standard position with terminal side at u. So this is what I just said in words. So here's your vector u. It's your unit vector, and it ends at xy, and that it's in standard position, so that means it's at the origin. Also, theta, we just said, is in standard position. So here's an example of theta. Okay, and its terminal side is at u. All right. Then u is equal to, which is xy, so we can rewrite that as the cosine of theta, sine of theta. Why? Well, I forgot my right angle here, but back to a couple units ago, right, we know that y is the same as sine of theta and x is the same as cosine of theta, so just making that substitution. And based off of our standard unit vectors, we can also now write that as cosine of theta times I plus sine of theta j. Okay, just to note, theta, that angle, is called the direction angle of the vector u. In most of these problems, we will be working in degrees. You will see that in a couple minutes. Okay. Oh, sorry, more notes. So in general, if vector v is in component form AB and it's a vector in standard position, and theta is the angle in standard position with terminal side at v. So again, here's your vector v ending at AB. Here's your theta in standard position. This is kind of a mini proof here. So look, I keep forgetting my rate. Okay. So, where was I here? So AB, all right. So I know that based off of my trig, right, that sine of theta would be equal to b divided by this length here, which is the magnitude of that vector b. So if I solve this for b, I know that b is the magnitude times sine of theta. Same thing with, let me jump to here, with the cosine of theta, right? I know cosine of theta would be adjacent a divided by the magnitude of v. So therefore a is equal to the magnitude of v cosine of theta. We also know that the magnitude of v, this hypotenuse, right, would be the square root of a squared plus b squared. So with that said, what I'm trying to show you is how can you rewrite v with this information. So I can take a, b, and again, write those with your standard unit vectors, ai plus b times j. By substitution, we know that a is the magnitude of cosine of theta, I. Same thing with b, that's the magnitude times sine of theta, j. You can kind of factor that out, and before we talked about how we can write that scalar outside, so it's the magnitude of v, and then in component form, cosine of theta, sine of theta. We need tan sometimes to solve these problems too, so we know that this is another mini proof. We know that tan of theta is equal to sine of theta divided by cosine of theta, multiplying technically by 1 over 1, right? So magnitude of v over magnitude of v. What's magnitude sine theta? Magnitude of v sine theta. That's b. And then magnitude of v cosine theta is a. So we also know that tan of theta equals b over a. And my phone is about to lose battery, so let's just move to my charger. Okay, here we go. All right, back in business. All right. So let's back up where we left off here. All right, so number 6. Find the direction angle for v equals 2i minus j. Where are we here? All right, so the direction angle, so we're just looking for theta. All right, so first of all, I need to figure out, well, which quadrant is this in? So 2i minus j, this isn't the best writing surface. We're going to be in quadrant 4 because it's 2 and then a negative 1. All right, and so we said that tan of theta is equal to b divided by a. So I'm going to take, right, because I can write this v, another way to write it is 2 negative 1, right? So I know that tan of theta equals negative 1 over 2. All right, so using our calculator here, we can take the tan inverse of both sides. You're going to find that theta equals negative 26.6 degrees. I'm going to grab my calculator just to verify that. So 1 minute here, make sure that you are in degrees. Okay, but because I'm in quadrant 4, okay, I'm going to take, really what I need is 360 minus the 26.6 degrees, which is going to give you 333.4 degrees, because we got to go like this. That's going to be your theta, and that's your answer. Okay, so the last two we need to talk about are word problems, and my thumb is in the view here. Okay. So, application of vectors, everybody's favorite. Maybe it is, maybe it's your favorite. So here's our first problem. A piano weighing 500 pounds is being pushed up a ramp into the back of a truck. The ramp is a board that can support 450 pounds and makes a 30-degree angle with the horizontal. Will the ramp support the piano? So things to remember is that work is an application of force through distance, and we know that work equals force times distance. Another thing I'd like to mention right now, because you might see it tonight on your assignments, they talk about vectors projected onto other vectors, and I just kind of want to draw this to the side for you. So the wording isn't used here so much, but if this was vector u, and we had vector v down here, again, you probably saw this in your physics classes, but we call this right here the projection of u onto v. You're like, what? Just keep that in mind. Might have to do a video if people struggle with the homework later on that specific type, but I needed to get that on the paper there. Okay, so let's draw a picture of what's going on here. So we have the horizontal, and then we have this ramp. Okay. And we know that the ramp is, the piano is 500 pounds and the ramp can support 450 pounds, and it's a 30-degree angle with the horizontal. So here's my 30 degrees. All right, and so you have this piano going up a ramp. All right, so things that we need to think about when we're pushing something, right? Because you're pushing this piano up the ramp. All right, so that right there, that's the force to move the ramp. Not move the ramp, move the piano up the ramp. Okay, this piano also has what we call the force due to gravity, force of gravity, which is the weight. All right, then, make sure I'm drawing this thing right. Okay. All right, dear. I want this is going to be a 90-degree angle here. And this right here is the force against the ramp. So think about pushing something up a ramp, everything that is going on there involving that activity. We need to figure out some angles. We know that this here is 30 degrees. Okay, this also is 90 degrees right here. So looking at this triangle right here, I know I have a 30 and 90, so therefore this is 60. Now if you look at this triangle right here, I have a 60 and 90, so therefore I know that this is 30. You could also show that by similar triangles. What I need to focus on is this triangle right here. So I'm just going to kind of pull that apart for a minute from the picture, just so we can see what's going on. Those are all degrees. Okay, so let's label what we know. Again, this is the hypotenuse. The hypotenuse. I didn't do a very good job recreating that. What else is new? Okay, so force of gravity, that's your weight. So this right here is 500. Because how do I know that? Because that's the weight of the piano. All right, and so they're asking, will the ramp support the piano? So what you really need to find is the magnitude of the force perpendicular to the board, which is the force against the ramp, which is this piece right here, which in my drawing is this. Okay, so part of the problem, it's not usually the math of actually solving it, it's more understanding all the pieces to these types of problems. So we're spending today and tomorrow on these types of problems just because it is kind of a more difficult topic. So now I have this right triangle, I can use my trig to solve for it. So I can use the cosine of 30 degrees, okay? That's your adjacent of x divided by your hypotenuse of 500. So when you do that out, so 500 times the cosine of 30 degrees, you should get approximately 433 pounds. So to go back to the question, it says that the ramp is a board that can support 450 pounds. So is it going to be able to support it? Yes, it will be able to support it, because 433 is less than 450. Okay, and the last one, I'm going to kind of go back to bearings again. A plane has a set bearing of south 60 degrees east at 600 miles per hour, but there is a wind blowing in the direction of north 45 degrees east at 80 miles per hour. What is the resultant speed and direction of the plane? So for a visual that is not drawn to scale, for people to see what's going on. So the bearing of south 60 degrees east. This is not drawn to scale. This is just for a visual, please. So here's your south 60 degrees east. Okay? And that's your plane. I'll just call that P. Then we also have the wind. That has north 45 degrees east. Again, that is not drawn to scale. That is the wind. And so north 45 degrees east, that's your 45 degrees. Okay? So they're asking, what is the resultant speed and direction of the plane? They're asking for, great line there, that vector and the information of that right there. So what we need when they ask the resultant speed, okay, we're really adding these two together. What's P plus W? Plane plus wind. So I need to go and figure out either the component form or what the standard unit vectors for the plane and the wind. So let's think about this for a minute. So let's look at the plane first. So we know that this should be 90 degrees, and I did a really bad job drawing that in. So if that's 60, I know that this is going to be 30 degrees. Okay, and so for the plane, so your magnitude, or what is this right here? What's that distance? What's the magnitude of that? That's 600 miles an hour, so that's our magnitude for the plane. Okay, so we have 600. All right, and now I need to bring in my theta. I need to figure out what theta is. So remember, theta is in standard position, so I'd have to go all the way like this. That would be your theta for this one, which is going to be 330. So I would have 600, and then I would have cosine of 330 degrees, sine of 330 degrees. Okay, and we want to simplify that for vector P for your plane. I might just pull I and J into this, I suppose. So if I simplify that cosine of 330 degrees, I have to multiply that by 600, so that's going to give you 300 root 3i. And then when you do 600 times your sine of 330, that's going to give you minus 300j. So that's information that I need after simplifying that. Now we need to do the same thing for the wind. Okay, it tells us it's blowing at 80 miles an hour, so that's the magnitude of that vector there. Again, we've got this. We need it in standard position. If this is 45, this is going to have to be 45. So for the wind, we have 80. And it's going to be cosine of 45 degrees, sine of 45 degrees. So again, bringing I and J into this. 80 distributed in there, we're going to get 40 root 2i plus 40 root 2j. So that's my wind vector. So it is asking, what is the resultant speed and direction of the plane? Okay, so we have to actually add those P and W together. All right, and so we will get an approximate answer of this. You want to use your calculator because we have some radicals here. So we should be doing 300 root 3 plus your 40 root 2. And so let's see. So when you do that, we should get approximately 576.18 I. And now for your J piece, we have a negative 300 plus a 40 root 2, and those are both your J's. So again, you're using your calculator, you should get negative 243.43 J. So that is the resultant vector, if this thing would focus. Now they asked us, again, I've said this 3 times, the resultant speed and direction. So the speed, that's just asking for the magnitude of my resultant vector. So what am I doing? I have to use my calculator and take root 576.18 squared plus your negative 243.43 quantity squared. And when you do that, again, I already have this done out, but you can follow along with your calculator. 625.49, and that's miles per hour, because that is what that piece of the vector is. So that is your speed, the resultant speed. And the last part, what is the direction? Okay, so for theta, I'm going to take the tan inverse. Okay, remember it's your B over your A. So I have my 243.43 and my 576.18. Okay, when you do that out, you're going to get 22.9 degrees. All right. But so thinking about where our resultant vector is, okay, we are in quadrant 4, so you have to take 360 and subtract your 22.9. That's going to give you 337.1 degrees. Or you could also tell me that's south 67.1 degrees east. Either answer would be okay if you wanted to actually figure out that piece there. Some people like this problem better than the force ones, but we're going to do what we can and reach out to me with questions.